quiet the crowd down. Hey, everybody. We're super pumped to have Vanessa Polito with us today. She's a scientist right now at Lockheed Martin in the solar and astrophysics laboratory. And if you didn't know that aerospace companies hire scientists, they do. There's information for you there. Vanessa was educated in Idaho, went to University of Cambridge, and was at the Bay Area Environmental Research Institute for a while. And I promised I would keep this brief, but we're really happy to learn about solar flares, and so I'm glad to have a world expert like you to introduce this to us. So thank you so much.
Thank you so much for inviting me. I'm actually really excited to talk to you about solar physics and solar flares. Can you see my screen?
Yes.
I think so. Okay, great.
It's not full. Yeah, that's my fault. I'll work on that. Yeah, go ahead.
Okay, so sorry, you see the screen full screen? I can start. Is that what you said? I didn't hear really well.
You're good. Go ahead.
Okay, great. So I know that not many of you are super familiar with solar physics, so I'm going to give a very broad introduction on the solar atmosphere and solar flares, and in particular how we study solar flares from using space-based satellites. And I will give just a couple of examples of recent research from my group, and I'll just conclude with some outlook on future missions and projects I'm involved in. Okay, so I'm gonna start by showing a very nice, movie of the sun. So these are images of a telescope that is called the AIA, that I will also talk about a bit more in detail later in the presentation. But basically what you're seeing here is the solar corona. So these are real images of the full disk of the sun taken in the ultraviolet wavelength. So what you're seeing is actually a false color because we wouldn't be able to see ultraviolet directly with our eyes, but we see them through UV telescope from space. And what you're seeing is actually emission at very high temperatures. So this is emission of very high temperature plasma, which I'll explain in a second what that means exactly, but it's basically emitted by an ion that is called iron 18, and it's plasma that is at very high temperatures, about 7 million degrees. So as you know, the sun and the stars are basically a ball of gas, and at these very high temperatures of million of kelvins, the gas is in the form of plasma. So basically it's made of ionized atoms and free electrons. So atoms like the ionized atoms, so ions like the iron 18, that means that it's an iron atom, which normally iron would have 26 electrons. But in the solar atmosphere, those very high temperatures, it's not in its neutral state. And what happens is that the electrons get stripped off, and you would have emission from ions such as iron 18, which basically means that it has lost 17 of its electrons. So I said this is the solar corona, so that means this is the outer layer of the solar atmosphere. So the solar atmosphere is made of different layers with different temperatures. And I'm going to show you a movie that goes through all of these layers separately. So what you're more used to when you think about the sun is probably the photosphere. So like the yellow, the yellow atmosphere that you see when you think about the sun. So this is actually the lowest layer of the solar atmosphere, the photosphere. And there's something very particular happening in the sun and all stars, that while you go outward from the photosphere to the outside of the atmosphere, the temperature increases, which is a little bit counterintuitive, because one would imagine that while you go away from a source of heating, the temperature should decrease. Instead, the temperature keeps rising from the photosphere outward. And after the photosphere, we have the layer above is called the chromosphere, where the temperature gets much higher to about 50,000 Kelvin. And then there is the transition region, which is a very thin layer where the temperature spikes very quickly in a very short space. And then finally we get the corona, which is what I was showing you at the beginning, which is a the hottest layer of the solar atmosphere. It's about 1 million degree Kelvin, which is about 10 to 6 Kelvin, but it can get to 10 million degree Kelvins or more during energetic events like flares. And while the temperature increases, the density actually decreases. So the outer layers of the atmosphere are very hot, but very tenuous. So this is actually one of the big things that people have studied in solar physics, and it's called the coronal heating problem. So why is the temperature getting so much larger going away from the source of heating? But today I'm actually not going to focus too much on coronal heating, but on something else, solar flares, as the title of my talk mentioned. So if you look at that brightening, that especially at the end of the movie, that's actually going outside my circle, I'm sorry about that. So that very bright emission is like what we call the solar flare. So you might have seen or heard about solar flares in the newspapers when we talk about auroras or northern lights. So these are associated with this beautiful phenomena that I think in October last year there were a few northern lights events that you could see very well from Washington State and Oregon. And those were associated with the flares and coronal mass ejection. Actually, these are pictures that I took from Svalbard, which is 1,000 kilometers from the North Pole, a couple of years ago. So just with my phone. So those were really beautiful observations of northern light. So this is great, but at the same time, solar flares can be pretty disruptive as well. They can damage satellites, harm human activity in space and on Earth, affect our electricity grid system, and so on. So this is one of the reasons why we want to understand how they occur, because they are really important and really affect our space environment. So yeah, I'm showing another movie of flare. So this is a more spectacular one. So you can see, I don't know if you can see my cursor, but it's a pretty obvious where it is. It's on the west limb of the sun. It's really strong, and the emission that we are seeing here, it's even hotter than the images I showed you before. So this is plasma dominated by iron 24s that is only formed in very extreme conditions where we have very high temperatures like 20 million Kelvin. So flares, as I mentioned, already are the largest explosions that we have in the solar system. So they're associated with the release of energy over a broad range of wavelengths. You can literally observe flares from gamma rays to the radio, and they affect all layers of the solar atmosphere that I was showing before. So they affect all the layers from photosphere to corona. And they release a tremendous amount of energy in a super short time. So flares can last minutes to hours, and they release energies which are energy which is orders of magnitude above what the most extreme phenomena that we can see on Earth. So obviously, as I mentioned before, one big reason to study flares is the space weather implication, but also theoretically, they're an ideal laboratory to study a lot of phenomena that occur everywhere in the universe. So flares occur in all stars, and they're related to mechanisms such as magnetic reconnection that I'm gonna talk about as well. Particle acceleration, shocks, turbulence, and all of these phenomena occur everywhere on the universe. But the advantage of studying them on the sun is that we have very good observations of the sun, and we can resolve these events very well, spatially, temporally, and spectrally, as I'm gonna show in this talk. So let's see, I'm gonna just briefly describe what is the general idea that behind flares. So this is a very simplified kind of cartoon, 2D cartoon of what that we use to kind of describe like this so-called standard flare model. So these green lines, are basically the magnetic field lines. So they go between one polarity and another. And so this is where it all starts. So it happens that two oppositively directed magnetic field lines come in very close contact with each other. And there is a phenomenon called magnetic reconnection. It's illustrated by this animation here. So basically, the magnetic field lines come in really close contact to each other and change their connectivity. So the potential magnetic energy that was stored into the magnetic field lines get transformed into different type of energies. So these are like just heating. So the plasma gets heated, so the temperature increases, and then heating gets transported via thermal conduction along the plasma. There can be waves. So these waves on this type of environment, like on plasma driven by magnetic field, are magnetohydrodynamic waves. What does that mean? So these are basically, if you imagine like the string of a guitar, imagine that is the magnetic field line. And when the string oscillates, the particles kind of oscillate together with the magnetic field, and the heating gets propagated along the field line this way. And finally, the particles get also accelerated from this region where we have magnetic reconnection towards the lower atmosphere. So this happens in the corona, so in the outer layer of the sun, but then the energy gets transported lower down into the transition region, chromosphere, and photosphere that I showed before, so the lower layers of the atmosphere. And the signature of this heating release is what we call flare ribbons. So they're basically these bright, elongated structures that we see here in this image that are visible in UV or optical wavelengths. And also we see X-ray footpoints, which are like a similar thing. So they are the roots of the flare loops, but they're more like small concentrated, what we call kernels that can be observed, for example, in X-rays. So these are like the lower atmospheric signatures of the flares. And then the last thing that happens is that the energy gets deposited in that plasma, but the plasma is not able to radiate away all of this huge amount of energy in such a short time. So what happens is that basically the plasma gets pushed upwards along the magnetic field lines because of overpressure. And this phenomenon is called chromospheric evaporation, which is actually a wrong name for it because it's not an evaporation in the sense of like change of gas state, but historically it has been called evaporation. But the idea is that you have plasma that is kind of going upward and filling those magnetic field lines. And the result is that you see those bright loops. So this is a real observation of a flare on the sun, and you see those very bright loops that are emitting at about 10 million Kelvin. So this is just the 2D view, but if you imagine that you are rotating this cartoon into 3D, rather than having just one flare loop and one foot point, you would have an arcade of loop and the flare ribbons. And these are observations of what this flare arcade will look like in reality. So this is the general idea. So it sounds like we have kind of understood everything, and we know what is happening. But in reality, this is a very sorry, were you asking something?
No, fascinating.
Oh. Okay, sorry. So basically, this is the general idea. Sorry, you have feedback. Maybe someone is unmuted. I don't know if, okay, maybe it's gone. So this is the general idea, but there are, of course, lots of things we don't understand about how the details of all of these things occur. So how the energy is released, transported, and dissipated, and how different energy mechanisms get partitioned into different energy releases and so on. So my work is mostly focused on comparing observations with models to try to understand the details of how these various phenomena occur in a solar flare. So I'm going to start by showing you some, talking about the observations. How do we observe flares on the sun? So I mostly focus on the ultraviolet wavelength range, and that is stopped by the Earth's atmosphere. So we need to go to space. So that's why I mostly work on space-based satellites. So lots of the movies I've shown so far, and probably if you have looked at the sun or like flares on the news, most of the times you would see images from AIA. That's the Atmospheric Imaging Assembly. Is a telescope on board the Solar Dynamic Observatory, which is a NASA mission. Was launched in 2006, and the AIA was actually built and is managed by my group at Lockheed Martin. And what it does is that it's taking full disk images of the sun continuously every 12 seconds with a resolution which is about like 500 miles on the sun. So different telescope filters will show basically different emission. That means different temperatures. That can mean that it's basically coming from different layers of the atmosphere, like I showed you at the beginning. So these are great. Images are great to have context of what we are observing and understanding what is happening during the flare, for example. But the main downside is that these are very broadband filters. So that means that they're observing a very broad range of temperatures and wavelengths. So this is an example in this plot of basically the dotted curve is the response function of the telescope as a function of wavelength. Just if you maybe some of you have not seen this symbol, the A with the dot, which you see a lot in these slides, is basically means angstrom. So it's like a unity of it's 10 to minus 10 meters. It's like 10 nanometers to be more clear. So these wavelengths are really broad. So that means that each of these filters of this telescope is looking at many lines at the same time. So we are not really resolving individual emission lines simultaneously. To do that, we need what we call a spectrograph or a spectrometer. So this is the instrument I work on mostly. I'm actually the deputy principal investigator of IRIS. So IRIS is the Interface Region Imaging Spectrograph. It was launched in 2013, and it's a small mission explorer, NASA mission. And what you're seeing here in the background is the same AA images that we were seeing before in the background. But then this insert is showing you basically what IRIS is observing in this small box while it's crossing the sun. So this actually was the passage of Mercury that we were capturing in front of the sun. So that's why this black dot here. But what I wanted to show in this movie is that you can see a very small portion of the sun, but the resolution at which we can resolve the details is very high. So IRIS is both an imager and a spectrograph. So that means that we can obtain images like AA, but on a very small field of view and just with the 4 filters. But at the same time, we can obtain we can resolve individual spectral lines. So more specifically, what happens is that, so here in this movie on the left, I'm showing the observation from IRIS, the images, and then there is this black line that is overlaid. And that's the slit of the spectrograph. So the light goes inside this slit and then it gets dispersed according to its wavelength. So it basically happens like in a prism, like you see here in the logo of IRIS. So the light goes through the prism and that gets dispersed into different wavelengths. And each of these, this is basically on the right, a screenshot of the CCD of the IRIS spectrograph. So you're seeing how individual spectral lines are captured as a function of wavelength. So why is that interesting to actually have spectroscopy? Because when you have individual emission lines, you can identify things like plasma motions and many other things you can't do with the images alone. So this is an example of an observation combining both information. So in the background, the gray movie is the IRIS images, and on the overlay, the colors represent the information we can get from the spectra. So different colors are showing if the plasma is moving towards us. So if it's blue shifted or if it's red shifted, it's going away from us. So this is like one of the things we can obtain when we look at the images. We can measure the velocity of the plasma, but we can also measure the line broadening that I'm going to talk about a bit more. You can measure relative intensity of different lines that might mean something when you are comparing with models and so on. So these are the type of observation that then we can compare with models to infer about the physical mechanisms that are occurring in the sun. So going back to the flare cartoon, so I will, if I have time, I will try to focus on two topics that I've been working on using Iris observations and models, and this is also work of my group at Lockheed, in particular postdoc that works with me, Juraj Lorenčík, that I'm gonna show is one of his latest papers in the following slides. Okay, so I'm going to start with the first topic, which is how we use high-resolution observations of the flare ribbons to understand about physical mechanisms in the flare heating during the flare, while the flare occurs. So since 2021, we've actually been observing at even very high cadence with Iris. We have designed this special sequence of programs that get spectra with a temporal resolution with a cadence which is less than 2 seconds. So this is an example of a movie of a flare that is basically, the background is again an image, a context image from the AAA telescope, the full disk one, and then the insert is showing these very small details that we can observe with Iris, the Iris images. So this insert is actually in negative colors, so that means that black is stronger than white in this case, so that might be a bit confusing. It's basically a reversed color scale to enhance the motion of those tiny brightenings. So these tiny brightenings are what we call kernels or foot points that I mentioned at the beginning, and they're like moving across the flare ribbon. So why are these interesting? So one thing Juraj did was to basically so take a screenshot of the images that I was showing before of the flare ribbons, and take a cut along this ribbon, so like the dotted line that you see here, and then if you imagine you straighten out this cut in y-axis, and then you plot the same cut as a function of time every 2 seconds in each frame that I was showing before. What you obtain is what we call a time distance plot. So actually the distance is on the y-axis and the time is on the x-axis. We did the same thing with the AAA images on the bottom, and you can see there is a stark contrast between the two. So like the Iris observations at that very high resolution show all these tiny brightenings and tiny features that you can see, and when you look at AA, it's like you're removing glasses, and then everything is way more fuzzy, and you're not able to distinguish those tiny motions. We measured so if you think about this is space and time, so the inclination of these curves give you a measure of the velocity at which these brightenings are moving. And we measured this with a series of techniques, and we found that these kernels are moving at velocities of about 2,000 kilometers per second or more. And this is very interesting because that's the first time we've seen this very high velocities. And sorry, I see I hear some echo. Okay, great. And this is actually the first time we see these velocities, and it's an evidence for what is called the sleep running magnetic reconnection model that was predicted about 20 years ago by different scientists, including co-author of this study that we work with from France, Guillaume Lanier. And this was not observed before because we didn't have these very high cadences. So this model this is just a representation of how the sleep-in reconnection works. So these colored lines are magnetic field lines that are moving very smoothly and very quickly while they reconnect. And basically, if you imagine that the bottom of this image is the sun, the solar atmosphere, where we observe the ribbons, you can imagine that the motion of this the imprint of the motion of these magnetic field lines are basically those kernels that we see sleeping. And just as a funny note, the name of the sleeping reconnection came from this cartoon of Willy Coyote, where like basically the idea is these kernels are moving as fast as the feet of the coyote. Another thing we notice in this observation is that we also have, those are just results based on images alone, but we also have spectra in this in iris, as I mentioned before, spectroscopic observations. So in this case, the slit was actually this showed basically marked by the, I don't know if you can see, there is a white streak or vertically crossing in the movie. This is where we have the slit of the spectrograph. So we do have some observations of individual spectral lines every time these kernels cross one of these slits. So what we find is that we took, in particular, we analyzed two lines. One is called silicon 4 and one is magnesium 2. These two lines are formed in the transition region and in the and in the chromosphere. So the magnesium 2 is formed deeper down compared to the silicon 4. What we did was to, we noticed that if you look at the intensity of the lines as a function of time, the silicon 4 is kind of peaking before the magnesium 2. So the intensity peaks before in one ion and then in the other one. And the delays between the two intensity peaks are very short, of the order of 1 to 6 seconds. So again, this is something we would have not been able to observe with lower cadence with the previous observations. So why is this interesting? Because the fact that these lines are formed in different heights of the atmosphere might tell you something about how the energy is propagating across the atmosphere. So to try to understand if we could reproduce these delays, we compare the observations with models. So there are different type of flare models that we use. In this talk, I'm just going to mention two models. The first one is the one that I mostly work with is what we call a 1D radiative hydrodynamic model. So the idea is very simple, is that we are widely simplifying the problem of a 3D flare by just assuming that a flare loop is a one-dimensional strand. So this is like a representation of what that means. The satellite is looking through the loop and we're just assuming that there is only one dimension. The fact that we are getting rid of the other two dimensions makes it much easier to simulate. We can focus on very specific small scale physics without worrying too much about the computation. It's not as computationally expensive as having a 3D models, but also right now there are no 3D models that are able to include all of the physics that we can include in 1D models. So the idea is that we have an energy release that we dump basically into the 1D model as a basically equation term. And the energy release can be the three type of energy releases we assume that are happening in flares that I mentioned in the introduction. So particle acceleration, thermal conduction, and magnetohydrodynamic waves. In particular, these are called Alphen waves, the ones that we usually consider for solar flares. And then we let the plasma evolve and respond to the heating, and then we can obtain things like temperature, velocity, density as a function of time and space along the loop. And then use this simulation to synthesize what the instruments will see. So basically, we can reproduce the observations in silicon 4 and magnesium 2 with the models. And without going too much into details, but what we did was then to take a grid of radin models with different heating mechanisms and compare with the results that we see in the observations. In particular, in the background here is a histogram of basically different time delays between the two ions, where the positive numbers means that silicon 4 is peaking before the magnesium 2. And overlay the symbols indicate the values that we find from the simulations, where EP models are like the particle acceleration model, assuming electron acceleration. TC is the thermal conduction only model, Alphen waves model, and H is a hybrid model with different mechanisms. And what we find is that we cannot reproduce the largest delays that we see with thermal conduction only. So that suggests that we need a non-thermal mechanism. So either particle acceleration, non-thermal particle acceleration, or waves. And even then, there are very few models that work to explain the long delays that we're seeing. So it's interesting because we are like, by comparing these very small delays with the models, we can provide very tight constraints on these flare models. So let's see how we're doing with time. Yeah, I think I can very quickly talk about another example of research that I've worked on. This is a bit more like started a bit earlier since I was doing my PhD actually studying the high temperature lines and chromospheric evaporation during flares. So I mentioned that when I was explaining this flare cartoon, that one of the things that are predicted from the standard flare model is the occurrence of this so-called chromospheric evaporation, where basically the plasma is going upward and filling these flare loops. So this has been predicted for many decades, and it has been observed early in the 80s with the earliest space satellites. But IRIS was really the first instrument that was able to resolve the chromospheric evaporation from the flare ribbons compared and isolated from the emission that you see in the flare loops because of its very good spatial resolution. Consider that the earlier observations in the 80s of these lines were like just one data point for the whole flare. There was no spatially resolved observations. But with IRIS, with the high resolution, we can really say, okay, this is plasma that is coming from the ribbons and is evaporating. And the fact that we can say that it's the chromospheric evaporation plasma, it's because the plasma is blue shifted. So when the plasma is coming towards you, as I mentioned earlier, it should be blue shifted. And for example, we saw this type of observations, like this is this very broad line here. It's called iron 21. Again, it's an iron atom that has lost 20 electrons. That only happens when the temperatures are very high, about 10 million degrees. This vertical line represents the position of the line if it was at rest. And instead, the peak of the line is shifted because the line is blue shifted. So this was interesting, but there is still something that we're still not understanding very well, that these lines are very broad, much broader than you would expect. What does that mean exactly? When we talk about broadening and non-thermal line broadening, we mean everything that is beyond what you expect from what you know of the plasma. So the non-thermal broadening is everything that is, if you subtract the observed broadening, the full width of maximum of the line, for example, and you subtract the thermal broadening, which is what you get if you only have the thermal motions. So the ions are moving very fast because it's 10 million degree plasma, so the higher temperature means higher velocity. So these lines are always broader than cooler lines. But still, even if you consider that and consider the instrumental broadening added by the satellite, there's still like hundreds of kilometers per second that we can't explain, that is way beyond what we imagine. And then another thing I noticed in an earlier paper was that the line was very symmetric. So I was calculating what we call red-blue asymmetry, so the difference between the symmetry in the red and the blue wing. And this was pretty symmetric. So the lines are broad and symmetric. So this is interesting because there are different mechanisms that people have suggested to explain the line broadening. So superposition of flows. If, for example, you are just you have a lot of these upflows along the magnetic field line. So B is the magnetic field in this case. And you are not able to resolve individual flows. So if you sum them all together, they will create a broader line that if you just looked at one strength. Another interpretation is almost the opposite. If you think again of those magneto-hydrodynamic waves, so like the guitar strings are oscillating, the magnetic field oscillating in the same way, and the ions are oscillating in that case perpendicularly to the direction of the magnetic field, you can also create a broadening, an extra broadening, or there could be some other mechanisms that do not have any preferential direction with the magnetic field. So in this first study, I was trying to understand if with the simulations we can explain just the superposition of flow, we could explain the observations. And the short answer is no. If you just imagine you take each of those like one loop, 1D loop strands, and you bundle them up together and you create a multi-thread loop strand, and imagine your satellite is observing across a number of strands, you can obtain a broad line, but that would be very asymmetric, which is different than what we see. So this is not the answer we're looking for, at least for this first study that I was doing. And something I've been working on the last few months, a year or so, is trying to extend this to a more statistical study. So I've looked at 7 different flares with different position along the across the solar disk that were observed by IRIS. And I was trying to understand if there is any correlation or any dependency of the broadening or the symmetry with the inclination of the magnetic field lines. And this is again because the three mechanisms have different predictions. So here I'm showing scatter plots of red blue asymmetry as a function of magnetic field inclination and broadening as a function of magnetic field inclination. And basically 0 means that you're looking perpendicularly to the magnetic field, so more like in the alpha wave case. So the broadening would be the strongest if it was driven by the waves. And parallel to the line of sight, so LOS is, sorry, I should have written it in the slide, is line of sight. So like, where is your satellite oriented compared to the direction of the magnetic field? If it's parallel, then you're basically looking straight along the magnetic field lines, and you should have the biggest broadening in that case, if it was caused by the superposition of flows. We didn't find a very strong correlation. The correlation factors are pretty weak. So we cannot say conclusively that there is one mechanism that is dominating with the other over the other. So for now, the conclusion is maybe there is a combination of multiple things happening at the same time, or maybe we need to extend the statistical study to more cases. And finally, I mentioned that there are different types of modeling that people can use to guide the comparison with the observations. So this is a very cool movie of a flare, a synthetic emission. So this is a computer simulation of a flare. It's not a real flare. This is basically the opposite of the 1D model I was explaining before. This is a 3D MHD model, magnetodynamic model. Here the different colors represent plasma emitting a different temperature that are overlaid with each other. And this type of models are very, they're very new. This model was actually published in 2019. They basically self-consistently generate a flare from magnetic reconnection, which is awesome. So this, the 1D models do not have any magnetic reconnection information or magnetic field information. It's just hydrodynamics. While here we also have the magnetic field. The downside of these simulations is that, first of all, they're really computationally expensive. It takes months to simulate a few seconds of a flare. And then since the scales are so much larger, it's hard to simulate small scale physics like particle acceleration or waves. So none of that is included in these models. But still, what we did here was to make a comparison between the observations and these 3D simulations, because for this type of question, this was the best model to answer that. So on the bottom here, I'm showing the scatter plot correlations between asymmetry and line broadening and velocity. And the top panels are showing the same scatter plots, but from the simulations. So the simulations reproduce a lot of the parameters of the observations pretty well. But one thing is strikingly different is the fact that in the simulations, we see that the lines are way more asymmetric again, like we saw with the 1D model, than in the observations. So the answer remains of what is missing in the models that might be making the lines more symmetric and broad. For example, the alpha waves turbulence was not included in the models I've shown so far, or possibly other mechanisms that we still need to figure out. So this is pretty much all I wanted to say in terms of examples of research, and hopefully you got a bit of an idea on how we study flares by combining observations and models. And I just want to leave the last couple of minutes to the future. So this is another movie of Iris observing an eruption on the limb of the sun. One thing that you can notice is that there's so much happening in this movie, and this Iris slit is just one line that can observe only a small range of locations as a function of time. So we're missing a lot of the dynamics that are happening in other locations in this event, because they're not captured by the slit. So this was the main motivation of the next mission we're working on, MUSE, the Multi-Slit Solar Explorer. It's a NASA medium-class explorer that was approved for launch in 2027. So we're currently working on building the instrument, but also preparing for the science of MUSE. So the innovative aspect of MUSE compared to IRIS and every other instrument before MUSE is the fact that rather than having just one slit, MUSE has 35 slits simultaneously. So for example, this is an example of what MUSE will observe. So it will observe a field of view, so a region on the sun, which is larger than than iris. We'll have a context image in the background, but overlaid here are the representation of what the 35 spectrograph slits will mean. It will mean that simultaneously we will be able to have spectroscopic observations on large field of view that will capture all the flare. Just to give you an idea, I like to show this movie. So this is the simulation of a flare, very similar to the one I showed before. On the top panel, I'm showing intensity of the plasma. In particular, this is iron 9, and the bottom panel is a Doppler shift map of the plasma. So blue again means that the plasma is moving towards us. This is actually a small eruption, like the ones that would drive the northern lights, and red means the plasma is moving away from us. So a single slide spectrograph will take quite a few minutes to kind of quite a long time to kind of raster through the whole region of a real flare. And as you can see, in the meantime, the flare has evolved and changed completely. So what we obtain is very different than what's in the reality. But with Muse, this will not be the case anymore, because it has 35 slits that simultaneously will allow us to kind of follow really closely the dynamics and understanding what's happening in the real sun, without missing on any of the action and any of the things that are happening in the flare. So yeah, this is pretty much it. My summary. I hope that I gave you a better idea of like what kind of things people study in solar physics. In particular, I heavily focused on solar flares, which is what I work on. So I showed some examples on how we can combine observations, high resolution observations from instruments such as IRIS with models to solve some questions. There are still many questions that remain open in solar physics, and hopefully many of them will be solved by the new instruments that we are preparing for. And thank you very much for listening. That's pretty much it for me.
Thank you. Vanessa, I know you have to run off shortly. Do we have any time for questions?
Oh yeah, I think as long as I leave maybe 2 minutes before 1, so maybe yeah, we can have a
Okay, good. We have plenty of time. Questions? Yes.
maybe I'll see you like better like this.
Try to be loud. Thank you for the talk. That was quite interesting. I actually had a conceptual question regarding magnetic reconnection. So, like when you say when a magnetic reconnection happens, there is dissipation of energy, but like you still need two plasmas moving relative to each other for magnetic reconnection to happen. So, like in the case of a flare, I can imagine one plasma moving, but like what is the second plasma with which it's colliding, or where the reconnection is happening?
Yeah, no, that's a really good question. So there are different theories, different ideas on how this can happen. There is observational evidence that, for example, the X point, that's what is called the magnetic reconnection point, there is like inflows of plasma that can get pushed together from the sides. So imagine you have like two motions of plasma that kind of squeeze around the reconnection region, and that facilitates the magnetic reconnection. So this is one of the ways you can obtain magnetic reconnection. It's resistivity problem as well. So it's kind of like there is a diffusion region where so the whole idea is that the plasma is in the solar atmosphere. So the magnetic field is kind of governing how the plasma is moving, because the plasma is always kind of rotating around the magnetic field line. So the plasma is kind of moving together with the magnetic field. But in the reconnection region, there can be also the other way around. The plasmas can drag the magnetic field lines because there are certain physical conditions that can occur all in those very specific places, and then that means if the plasma is dragging the magnetic field, it can facilitate also the magnetic reconnection. I don't know if that makes sense. If you answer your question.
That helps. Yes.
It helps, yeah. So a coronal mass ejection then is basically just too much energy has been dumped in, and so it just blows a big bubble. Is that basically it? And how much?
Yeah, so the coronal mass ejection can be related to a flare or not. So there are flares without coronal mass ejections, and there are flares with coronal mass ejections. So if you, for example, see that movie yeah, the cartoon I chose didn't have the CME, the coronal mass ejection cartoon, but basically, for example, I'll show again very quickly the this movie that I was showing. Maybe it's this one. So this, you see this thing lifting and then it breaks and it opens. So that would be, this is a simulation, so it's not a real CME, but the CME part would be basically this this structure that is lifting from the atmosphere and then it breaks. So it is related to the flare. What it is practically is called, it's an eruption of what we call a flux rope. So there is a magnetic, so there is a bundle of magnetic field lines that is called the flux rope. So if you imagine the cartoon that I showed in 2D, if you rotate it, the flux rope will go through the magnetic reconnection in 3D. And actually, I can show this again, which might make it easier to understand. Hopefully, where is it? So I didn't show, there is no flux rope in this cartoon just because, I don't know, I just showed this one for simplicity, but imagine the CME will be, I think I can annotate. Let's see if I can manage to annotate. Imagine the, oh no, okay. I don't know if I click on it, it's kind of changing the slide. So I'll just do it with the cursor without annotating. But imagine there is like a bundle of magnetic field lines that is going across the flare arcade like this. And then those like round parts here of the arcade will be pushed so much by this flux rope that is trying to leave the sun. It's it's kind of trying to go away from the surface of the sun and more outwards, and it's gonna have so much strength that it will break this magnetic field lines here and escape into the solar system. So basically, the idea is that the coronal mass ejection is can happen at the same time as the flare when the flare is eruptive, but that doesn't happen for all flares. Sometimes the flares just stay confined, and like in this picture here, there are no obvious coronal mass ejections, but that movie I was showing before, for example, had this like big kind of eruption that happens, and that's a bundle of magnetic field lines called flux rope that is erupting from the magnetic reconnection region and breaking through the arcade and leaving the sun. I don't know if this makes sense. It's kind of hard to explain online without a whiteboard, but hopefully you get the gist of it.
Without a three-dimensional whiteboard. Yeah. Anything else? All in all, I'm terrified. The flares. I don't want to be there during a flare. I don't see any more questions. Thank you so much. It was we all learned a lot, I'm sure, and thank you so much for taking time out of your busy day to give this talk.
No, thanks to you.
Okay. Yeah. Bye. We're gonna do the Zoom thing.